Okay, we have done two problems. The previous problem, the second problem, I couldn't finish it, but I have noted the last answer. The peak inverse voltage is 5 volt. So you can look into this green lined one here. Just I am giving you hint. Try yourself. The voltage across D1. Here we can see that D1 is reverse biased. So the peak inverse voltage means the voltage across the diode, reverse biased diode. So VD1 is equal to VAC, which is equal to, since A and D are in the same potential, V voltage across AC will be same as voltage across DC. So VAC will be VDC. The voltage across DC is the output voltage in this circuit, that is 5 volt, which we are already obtained. So peak inverse voltage is 5 volt. The same case you can have for this one, that is when D2 is reverse biased during the positive half cycle, D2 is reverse biased, and you can see that the voltage across D2 is again 5 volt. So the peak inverse voltage for D1 and D2 for this second problem is 5 volt. Now let's see the third problem. Let's read the problem. In a circuit given below, the maximum secondary voltage is 136 volt. That is, here we are applying 230 volt RMS value, and we are getting not the RMS value of voltage, but we are given with the maximum secondary voltage is 136 volt. That is, Vm is 136. Now we have to find the DC load voltage. So load is given here, the voltage across the load we have to find, that is, this is the load. So voltage across this one we have to find, and also the peak inverse voltage, that is voltage which appears across the reverse biased diodes. You know that during positive half cycle, this diode, if we name these diodes as D1, D2, D3, D4, then during the positive half cycle you can see that the D1 and D3 are forward biased if this end is positive and this end is negative, and the D2 and D4 are reverse biased. So we have to find the voltages across the reverse biased diodes to find the peak inverse voltage, and also the output frequency. The frequency of the input signal is given as 50 Hz, so we have to find out the frequency of the output signal. So let's note down the given quantities here. Vm of the secondary of the transformer is given as 136 volt, and frequency of the input signal f in is given as 50 Hz. So now we have to consider the different half cycles. Let's consider the positive half cycle, that is the upper end is positive and the lower end is negative. I am naming this is a convention, only you can use during the positive half cycle the lower end is positive and upper end is negative, no problem. But for the sake of our convenience and the convention which we are following throughout the is curriculum, the upper end is positive and the lower end is negative during the positive half cycle. So I am denoting only this part here. During the positive half cycle, if you look into this one, D1 is forward biased, D3 is forward biased, and D2 and D4 are reverse biased. So just remembering the position of D1 is forward bias, so it is replaced by a short, and D2 is reverse biased. I am replacing it by a open circuit, and D3 is forward biased, and D4 is an open circuit, and across which we are having the load here, and here also it is grounded. That means they are connected like this. So this one I am replacing this part, I am connecting directly, so it will look like this. For easy convenience, I can take this like this, so that this part can be erased. So I am naming these nodes as the previous case. Also I am naming the nodes as A, B, C and D. So here this will be A, this will be B, this will be C, and this will be D. Now first of all, let's see the peak inverse voltage. Let's calculate the peak inverse voltage. The second part we are doing first because it is easy. The peak inverse voltage is equal to voltage across the reverse biased diodes, that is VAD, the voltage across the diode. And we know that the voltage across this terminals A and B is the peak input voltage, that is Vm. So VAD, if you redraw this diagram, you can see that A and C are in same potential. Then across we are C and D we are having this one, and D and B are in the same potential, and we are having A here, C is here, D is here, and B is here. The diode voltage across the diode D2 is V, peak inverse voltage VAD. The voltage across VAD and VBC. So BC will be equal to VAD, since D and B and D are at the same point, they are at the same potential, so voltage across AD will be same as voltage across AB, which is equal to the Vm value. So peak inverse voltage is equal to 136 volt. The same case for VBC, because across which we are having the diode D4, so D4 VBC will be equal to VBA, which is again 136 volt. So the peak inverse voltage will be 136 volt. Now we need to, from this one we can directly write the voltage across the with DC voltage across the load resistance is again whatever the voltage across A and B will appear across this CD, that is, this is the V output. So across which the DC voltage is given by VDC will be equal to 2 Vm by pi, which is equal to 2 into, since the voltage AB is Vm, so VCD will also be Vm, and the DC voltage will be 2 Vm by pi, so 2 into 136 by pi. Substitute this value and calculate this value and represent in terms of V, and again comment the final answer to this question in the Google Classroom. So this will be the second video. So for the second video, comment the answer to this question in the second part in the Google Classroom for the second part. So this is the assignment for you to make your ensure your participation and involvement in the classes. So now we still have one more part. So this is the first part of the question, that is, what should be the DC voltage. For the second part, peak inverse voltage we have done, then the output frequency we had to calculate. That is the third part of the question. But you know that this is a full wave bridge rectifier. For a full wave bridge rectifier, I'm not going to discuss the entire part, but you can see why. For a full wave rectifier, this is F out will be, frequency of the output will be equal to 2 times frequency of the input signal. Why it is I am not discussing here, because it is already discussed in the theory part, but while doing the calculation, this is the reason for this is that since it is a full wave rectifier, we can write F out is equal to 2 times F in, so which is equal to 2 into 50, which is equal to 100 Hertz. So this is the third part of the question. So now let's look into the next question. This is another question. Let's read the question. Determine the voltage available from the voltage doubler if the secondary voltage of the transformer is 120 volt RMS. So you are asked to find out the output of the voltage doubler if the secondary voltage of the transformer is 120 volt. That means we are given with a input Vrms is equal to 120 volt. Now you know that for a voltage doubler, V out will be equal to 2 times the maximum voltage of the input signal or peak value of the voltage signal Vm. So V out will be 2 times Vm. From the input Vrms, Vm can be obtained as, you know, Vm is equal to root 2 Vrms. So which is equal to Vm is equal to root 2 into Vrms, which is equal to root 2 into 120, which is equal to, if you calculate it, you can see that it is 169.7 volt. Can also try it, 169.7 volt. Now V out will be 2 times this value, that is 2 into Vm, which is equal to 2 times 169.7 is equal to dash volt. Again, make a second comment to this video by answering this value. That means you have to write the numerical value of this question or the final answer of this question as a second comment to this video. So today's video, first video, you have to comment for the first question. So for first one you have to write down the numerical value of this and that answer. Here for the second video you have to make 2 comments. One is for the answer to the fourth question and third question, and another is the answer to the fourth question. So that is the fourth one. So 2 comments you have to make for this video. The answer to the second part of the third question and answer to the final answer to this fourth question. Then let's see the next question. It is again with respect to a doubler. Determine the required peak inverse voltage ratings of the diode in terms of the peak secondary voltage Vm. So we want to, there is no numerical values here. Here you are asked to determine the required peak inverse ratings of the diode in terms of the peak secondary voltage Vm. That means the secondary voltage of the transformer is given as Vm. Now if you want to make a voltage doubler, then, or if you want to design a voltage doubler, you have to use 2 diodes and 2 capacitors and make sure that depending upon this Vm value you have to choose the proper capacitors and proper diodes with peak inverse values. So here you are asked to find the peak inverse value of the diodes. So I told you to find the peak inverse value of the diodes, we have to measure the voltage across the diode when it is reverse biased. For any circuit, to find the peak inverse voltage means find the voltage which appears across the reverse biased diodes. So here we are given with the secondary voltage as Vm. Secondary of the transformer is Vm. Now to find these peak inverse voltages, I am considering the equivalent circuit of this one. It is again a voltage doubler circuit. So I am considering the positive half cycle first. So during the positive half cycle, suppose the upper end is positive, then C1 will be like this, and the diode D1 is forward biased and diode D2 is reverse biased, so it is replaced by an open circuit. Then C2 is here. So this is the here is the D2, here it is C1, Vm is the voltage. Then during the positive half cycle, this also charged to Vm with a positive here and negative here. Here it is again positive, here it is again negative. So this is the state. So this can be written like again I am redrawing like this plus Vm I am replacing it by a DC source like this just for convenience, and the diode capacitance C1 is charged to maximum value, so it is also having a voltage Vm, here also Vm, and then we are having C2 here. Across these 2 points we are having D2, so voltage across D2 we have to calculate. This is C2. This C2, you know that the output voltage of C2 is 2 Vm. Now from this diagram, this voltage source Vm and this voltage source are connected back to back, not in the aiding format, or voltage of this capacitor does not aid the voltage source, because here we are having a connection like this. So plus and plus are connected together, that means they nullify, and the voltage at this node will be definitely 0, and here the voltage at this node is 2 Vm. So potential difference, suppose I am calling this node as A and this node as B and this node as C, the voltage across the diode D2 will be equal to voltage across AB, which is equal to 2 Vm is voltage across AB is voltage at B minus voltage at B minus voltage at A, which is equal to 2 Vm minus 0, which is equal to 2 Vm. So that is the voltage across the second diode. Now to find the voltage across the peak inverse voltage, which is the peak inverse voltage of D2. So D2 must have a peak inverse voltage of 2 Vm. Now consider to find the peak inverse voltage of the diode D1, consider the negative half cycle. So during the negative half cycle, this diode D1 is reverse biased and diode D2 is forward biased. So to have this one, let's redraw the circuit like this. We are having during the negative half cycle, we know that the capacitor during the positive half cycle, it is fully charged to Vm, so it can be represented like this. And here it is negative and here it is positive, so it is negative and positive. The signal voltage is like this. Diode D1 is open because it is reverse bias. Diode D2 is closed, and here we are having C2, the capacitor C2. This C2 will be having a charge of 2 Vm, and here it is having a voltage as Vm, and here it is having a voltage of Vm, and here the node A, here our node B, here our node C in the previous case. The same convention we are following. So then peak inverse voltage of D1, that is here our diode D1 is connected, is equal to D1, I am calling it as D1, which is equal to VAC. But VAC will be the voltage across AC will be equal to voltage across BC, since A and B are at the same potential VBC. So VBC will be equal to voltage across the second capacitor C2. The voltage across the second capacitor, because across BC the second capacitor C2 is connected, which will have a charge of voltage of 2 Vm. So again V equal to Vc2 is 2 Vm. So the peak inverse voltage of D2 is obtained as 2 Vm, and peak inverse voltage of D1 is also obtained as 2 Vm. So this is the way we can calculate the peak inverse voltage. Okay, thank you.